So I hope you guys have thought about what rebates R1, the rebates R1 and R2 need to be in order to guarantee one, that rad is in equilibrium, and two, guarantee that rad is the only equilibrium. So if you have understood how to, if you could answer this, basically you're on a good way to understanding game theory. So if we start with R1, or if we start with the first point here, to get what R1 and R2 needs to be in order for rad to be in equilibrium, then R2 has to be bigger or equal to 0. So we need to know that R2 has to be better than. So if I say it like this, if I clam up and assume that the guy, my partner, is selfish and he would rad, I would probably be looking at 10 months. And in order for me to know that rad would be a good alternative for me compared to clamming, then I will need to know that I would get at least, it would be at least as good as 10. Because that's the thing, and that's the thing that really also surprised me, because I would normally think that R2 has to be bigger than 0, so it has to at least be 9 months, and the rebate has to be at least 1 in order for me to, then this would obviously be better than 10. 9 is less than 10, but a Nash equilibrium says that you need to choose the strategy that is at least as good as all the other strategies. So it could be the same number according to the Nash equilibrium, and it would be an equilibrium. So to answer the question, R2 has to be equal to 0 or bigger than 0. And also, obviously, if you're a prosecutor, you would normally give a prisoner a plea bargain that is more than 0, because you want to give the prisoner incentive to tell you something. So in a normal, logical situation, it would be probably bigger than 0. But according to the Nash equilibrium, the strategy that is chosen has to at least be as good as all the other strategies. So not better. So that was something that really got me like, what? That doesn't really make sense. But in the real world, as I said before, a prosecutor would probably give something to give incentives to the prisoner. And to guarantee that rad is the only equilibrium, here obviously R2 still has to be either equal to 0 or larger than 0, but R1 has to be bigger than 10. And this is because in order for it to rat to be the only equilibrium and not clam be an equilibrium, it has to be bigger. It has to be better than getting 1 month in prison. So if this would be 9, it would be the same, and then we will have more than 1 equilibrium. Excuse me. So in order for it to be the only equilibrium, we want R1 to be bigger than 9, so 0. So we want it to be bigger than 9. So basically 10. So we get 0, if that makes sense. Okay, so we have done the first game, and we will continue the second game. But in this, just to elaborate and just to clarify, so in the prisoner's dilemma, we had one equilibrium. Okay, and let's go to the coordination game. The coordination game. Okay, so first I want us to envision a situation where cars meet on the roads as normal, and in some countries people keep to the left, and in some countries people keep to the right. So if they go left right, they would obviously crash. So we also want to think that the choices they make are simultaneous. They don't know which way. Like, for example, obviously if you're in a like plain road, you would see, and you could maybe make a choice to go left or right to avoid a crash. But if you're in a curve or a top of a hill, it's impossible for you to know. You will meet on the top of the hill and you will crash if you're on the opposite sides. So yeah, and another thing in the Nash, when it comes to game theory, when we say simultaneously, we just means that it's impossible for the other party to know what you will do. So before you can make your decision. So in this case, it's impossible. They're on top of the hill and they crash because they can't see nothing. They can't see anything. Okay. So let's try to represent this as a game, and let's make it as simple as possible. So in order to conduct this as in a normal form, we have first we have players. So in a normal form, we have to have players, strategies, payoff. So number one, who's the players? We have driver one and driver two. Strategy sets, we have either you go right or you go left. Payoff functions and outcomes. That's something we can ourselves assign. Or also crash and pass. Oh, okay. So yeah. So the matrix is very self-explanatory. If you go left, if driver one and driver two goes left, they will pass each other. If they go left, right, they will crash. If they go right, left, they would crash as well, and right, pass. And to try to illustrate this in the most simple way as possible, we assign 1 and -1 as utility or payoffs. So if we go left, obviously for both drivers, that would be a good thing. So we have 1 and 1. And if we go right, left for both drivers, it's not a good thing. If we go right, left for both drivers, not a good thing. They crash and get injured. And also right is a good thing, so it's a positive payoff or utility. So what outcome should we predict? So we use the Nash Equilibrium. And how do we find this equilibrium? Well, we use best reply analysis. So the first, okay, so if we look at player one first, obviously for player one, the best thing is to go left if driver one goes left. So we underline here, and it's if it would be optimal for driver one to go right if driver two goes right. So it's underlined. So these two are underlined. Okay, and then we will do the same for player two, and it's exactly the same. So left if driver one goes left, and right if driver one goes right? So basically it's the same. So what do we have here? We have, in the first game we had one equilibrium, and now it seems like we have two equilibriums. So we have two equilibriums here, left, left, and right, right. So in a situation like this, how would we think about this? How would we try to mend the situation if we have several outcomes as several equilibriums? The problem is only one outcome will actually happen. So which equilibrium will be played requires some form of coordination. Somehow all players need to come to understand what will happen. So how could we make coordination? So there's two different ways here. And so if we take the first one, dominance, and obviously in the prisoner's dilemma we could see dominance happen automatically. So they use ration, and one strategy was better than the other. And in that case, that was what happened, rat in the prisoner's dilemma. Number two is pre-play communication. So we could, they could pick up the phone and say, "Yo, listen, I am driving this way, you're driving this way, and if we meet each other on the roads, you know what, just stay on the left and I'll stay on the left just so we don't crash." So if it's a small village or yeah, if it's a small community, you could do that. Maybe it's not optimal, but that would be a thing to do. Self-enforcing agreement, no time on the road. So you could try to have a communication when you're on the road, but also that would not be ideal, because if you're on the top of the hill, you can't really communicate. The crash would already happen if you're on the wrong side of the road. So yeah. But number three maybe would be, in this case, the optimal or the logical thing to do. So if people drive in Sweden, we drive on the right side. So if we drive on the right side and we have some people driving on the left side, let's say that we have 90% driving on the right side and 10% driving on the left side. There will be multiple accidents, making people understand, okay, I can't really drive on the left side, so let me just switch so I can avoid a situation where I'm injured. So that's the case of learning, and that would maybe be logical in this case, I would assume. So yeah, so that's maybe, so these are three points where coordination could happen, but I would say number three would be the logical point in this situation, at least. So if you have any other points, let me know in the comments. So convention, social norm, that's exactly what I said. So it's a good thing to Google. If you guys want to Google convention, social norm, in Sweden we just drive on the right side, and that's the norm. So if you drive on the left side, you kind of deviate, and you would most likely crash or get into an accident eventually. So yeah, so just to go back, so prisoner's dilemma, we had one equilibrium, and in the previous game, we had two equilibriums, right? So now we go to a game called chicken. I don't even like chickens, but chicken. Okay, so here we have another situation, single lane bridge, where driver head for a single lane. They come from opposite directions. So so I have basically three different situations. Either they can continue. If both continue, they crash, obviously. If they both stop, both will be delayed. If one stops and one continues, one is delayed, but the other one can pass without delay. So I want you guys to think about this situation, and we can put it in a game. And to make it a game in normal form, we have to have players, strategies, and payoffs. So player one is, or players are driver one and driver two. Strategy sets is continue or stop. And payoff functions and outcomes, something we could assign. Our payoffs functions is something we can assign ourselves. So yeah. So here we have outcomes. So yeah, if for instance, if driver one and driver two both stops, they're both delayed. If player two continues and player one stops, player one is delayed and player two passes without delay, and etc. And we can assign payoffs to this, so we're making this as easy as possible. So obviously if we stop and we both get delayed, we get 0. So I have three different utility scales. We'll have 0, 2, and -10. So 0 is delay. 2 is obviously pass because it's the best option. And we have -10 in crash. So 2, 0, and -10. So yeah. So we have these three utilities. And what we want to do now is to find the equilibrium. And how do we find the equilibrium? Well, we use best reply analysis. Analyze. Best reply function. So we find the equilibrium. Yeah, okay. Oh, my bad. So, okay. We find the equilibrium. So, obviously here, the best thing for player one to do is to, or driver one, is to stop if driver two continues, and to continue if driver two stops. So we have this is the equilibrium. This not the equilibrium. This is the best reply for driver one and driver two. And then we have the same for, we do the same for player driver two. So he should stop. He should stop if driver one continues, and he should continue if driver one stops. So we have two equilibriums here as well. I have two equilibriums. So continue, stop, and stop and continue. But this is because in the previous game with the previous game with where they were meeting on the top of the hill, where they could crash, they also had two different equilibriums, but it's not exactly the same situation here, because this situation is asymmetric, because despite both players being in the same situation, one is better off than the other. They have to behave differently. So one continues, one stops, or one stops and one continues. And because of that, they will receive different payoffs. So we can go here. So if one, in this equilibrium, driver two has a higher utility than driver one, and here driver one has a higher utility than driver two. So there is a difference here, and it's an unfair situation in equilibrium, yeah. So then we have, obviously there's different social norms as well. That also is not fair. For example, if in some cultures they let women cross first or pass first and let them continue, and a man stops, or an older person in some cultures, they let them pass, or maybe I'm spitballing here, but maybe a pregnant person as well. So there's different conventions or social norms, and this is a part of coordination. So this is something we touched on in the previous game as well. And also they can use a coin toss to see if one should go, or one should go and one should stop. But obviously they could, but that would take a lot of time, and not maybe the optimal way to, wouldn't maybe be the optimal way, but still they could always call each other and say, hey, if we will probably meet in this situation, in this road, I want you to stop. But obviously the other person would be like, no, I want you to stop because I have a meeting to go to. Or like, why would they, like the other person would always say no, because it's an unfair situation. One needs to stop and one needs to continue. So how would a person say okay to that, if he's not nice? Maybe there is nice people out there, but yeah, we assume that people are want to maximize their utility and don't want to be delayed. So yeah, and also the young let old pass first, and pregnant ladies, and maybe women, etc., as I said before. So yeah, we have a football. Okay, this is the final game that I want to speak about. We have a situation where we have a penalty, where we have two players, so shooter and goalkeeper. So shooter and goalie. Shooter decides which side to shoot. Goalie decides which side to defend. Simultaneously choices. Some people, and there's a question mark here because some people would assume that maybe this does not happen simultaneously, because a goalie would know whether, because he could maybe see that the player would go right and he would defend right. But in a normal situation, or in a game, a soccer game, everything happens so fast. So it's not, so we kind of see it as good as simultaneously, because it's impossible for the goalie to know which way the shooter would shoot in such a small amount of time. So obviously in literal sense is not simultaneous, but in game theory we mean simultaneously. That is simultaneously if the goalkeeper could not predict what way the shooter would, if he would go right or left. So in that case, it is as good as simultaneously. So maybe literally not simultaneously, but in this sense, it's impossible for the goalie to know, okay, should the shooter go, because everything happens so fast. So yes, to answer the question, yes, it's simultaneously. Yeah, so we have, we're doing the game. So we have players, we have strategies, and we have outcomes, utility levels. Okay, so this is very self-explanatory and very easy. So that's how you should make it. So maybe it's the optimal way to show this, so it's easy to understand. So we have, obviously, if one shoots, if the if the shooter shoots left and the goalie defends left, there's no goal. And if one goes left and one goes right, it's goal, and it's the same for the other two below. So we assign payoffs to them, -1 and 1. So obviously for the shooter, there's no goal, so it's a utility number of -1. And for the goalie, it's a 1 because it's no goal. And it's the same for the others. So now we want to see where the equilibrium. So how can we find the equilibrium or the Nash equilibrium? Well, best reply, analyzes. Basically, we analyze the best reply for each player. Okay, so find the equilibrium. So I want you guys to find if you pause the video for just a second and just look at this matrix and just try to figure out and use the best reply function and see which one is the best one for each player, and then find the equilibrium. Okay, hopefully you guys are back and took a second. Yeah, so we have so here obviously if you look at player 1 first, the shooter, for him we have an equilibrium. We have an equilibrium here, and we have an equilibrium here. So these two, not equilibrium, not equilibrium, but it's the best reply. It's the best option. This box and this box is the best option for the shooter. For the goalie, we have this box and we have this box. So what does this mean? It means we have no equilibrium. We have no equilibrium because there's no joint. Everybody has their own boxes, so no equilibrium exists. So, and in this game, because this penalty game is within another game and is extreme competition, so they can't really use coordination because they can't really communicate or collaborate in one way, because one player's gain is another player's loss. So it's a zero. In other words, it's called zero-sum game. So in this game, players aim to not be predictable. So they do not want to be predictable. And also that's John Nash, what he won, in very simple terms, what he won a Nobel Prize for. So he said that if there's no equilibrium, if we enforce them to not act predictable or act unpredictable, it would force an equilibrium. So an equilibrium would emerge if we give the players the option to be unpredictable. So in very simple terms, but yeah. So let's say that the goalie tosses a coin. So if shooters go left, the probability of a goal is 50%, and if shooter goes right, probability of a goal is also 50%. So it's always 50%, independently of which side the shooter goes. So it's always 50%. And let's say expected utility for both of them, if they toss a coin, is 0, independent of which side the shooter would go. So yeah, let's introduce this and say, okay, the goalie tosses a coin, and we assign the utility 0, 0. And then we have a new game with this additional points. Okay, and then we would say the same thing for the shooter. What happens if the shooter tosses a coin? Well, the probability is the same, 50%, independent of which side the goalie goes. So, and we assign a expected utility to both 0, independently of which side the goalie goes. So here we have introduce also a new matrix, or we add that the shooter also can toss a coin. So we have a new table, and this would help us find an equilibrium. Okay, so here we have, okay, we could go step by step. So how we find this is basically the best reply function. So we look at, okay, what is the optimal for player 1, for the shooter, and for the goalie. So we have, we can look here. So 0, so 1 here, and then if he tosses a coin, this is also an optimal point, and this is also an optimal point for the shooter. And then we have, if he tosses a coin, then we have 0. So here we have a new equilibrium. So when they toss a coin, basically they are forced, an equilibrium will emerge. And this is what John Nash said, that if we enforce give the players room to be unpredictable, and it would force an equilibrium into existence, if that makes sense. So allowing players to toss the coins restores equilibrium, as I said. And this is true in general, but we need to also allow players to choose probabilities in different ways, alternative freely. And this is, so maybe not 50%, maybe sometimes 75%, 35%. And also actually there's researchers that have looked into this empirically and seen and done studies about this. So they have analyzed football games, I believe, and seen how people, their actions, and how they behave. And empirically they have, I think I'm correct, they have found that people, that this is a thing. And obviously this is a thing because John Nash won a Nobel Prize for it, but they have empirically proven this. So yeah. So in real life, do people really toss coins? Well, not so. So also we should not see it as literally. People don't really toss coins like, wait, let me just toss a coin before you shoot the penalty. It's not, but they should act as if it's random, as if they toss the coin. So they should try to be unpredictable, and they should behave as if they toss the coin. And yeah, maybe if the goalie looked up to the stand and seen, okay, if somebody wears blue, I would go left, and somebody wears red, I would go right. So that would be a thing, maybe, I don't know, but they should, so literally they don't toss coins, but they should behave as they toss coins, so random, basically. So yeah. So mixed strategies, existence of equilibrium. If game has finite many players, each player has finitely many strategies, then the game should at least have one Nash Equilibrium, possibly in mixed strategies. So yeah, that is all I have to say for part 2. And in part 3, I will have a problem set that I will work on. And I want to remind you guys that I am a master student, so this is my is a recap for myself. So if I said anything that you have a question about, if something is if you're wondering about something, write me in the comments, and I'll make sure to reply. So yeah, thank you guys for listening, and I will see you guys in the problem set we will do together. Thank you.